In this lesson, we will be looking at permutations, combinations, and the binomial theorem. In this lesson, we'll be looking at how to permute objects that have identical items in them.
So in a previous lesson, when we were looking at permutations, I tried to make it very clear that what we were looking at were unique orderings of objects is something we call a permutation. Now, in the previous lesson, that really didn't amount to much because the permutations were going to be unique regardless, okay? Because all of the individual items were unique in themselves, and so any particular ordering of those items was going to be unique as well here. But that is not always the case here, and that's what we're going to look at in this particular lesson here. What we're going to do here, it's important to note that this is not a restriction that we're imposing on a scenario here. This is the result of objects being identical, okay? So when you've got repeating objects, okay, then what we do to find the number of permutations is we take the total number of objects factorial, okay, so n is equal to the total number of objects. And then what we're going to do is we're going to, if we've got a of them that are identical, then we're going to take n factorial, we're going to divide by a factorial. If b of them are identical, we're going to divide by b factorial. If c of them are identical, we'll divide by c factorial. And I'll show you why in just a minute here. But this is the way that we approach those particular items here that are being repeated. Now let's look at an example of how this idea develops here, okay? This isn't going to necessarily be a proof, but more like an indication as to what's actually going on here. So let's take the letters in the word to, okay, TWO. There are three of them, so there are three factorial ways that you could organize them, and here are all six of those different permutations. Okay? Now, what we're going to do here is we're going to take the letters in the word to, and we're going to simply replace the W with an O. Okay? And let's take a look at how many permutations you get when you do that. Okay? Because now we've got two objects that are not distinct, okay? These two are identical here. So TWO becomes TOO. TOW becomes TOO. Well, these two are identical. Now, if you compare these two, okay, really what we did is we left the T out front and then we just permuted the two of them there. But every permutation of those two letters was identical, okay? Down here, WTO and OTW, those two different permutations, again, if you let W become O, they look exactly the same. Now let's just think about what's going on here. You take the T, you leave the T in the middle, and you just permute the two letters around it. You get two different permutations here, but they end up being identical over here. And then the same argument can be made down here, WOT, OWT. Okay, if you change the W to O, we get OOT, and that's like leaving T at the end and then just permuting those two letters in front. So what happens is the number of different ways you could I should say it like this. I want to be very clear with this. The number of ways you could permute two identical letters has basically been eliminated. So we're going to take the total number of permutations, okay, of the three letters, and we're going to divide out the number of ways you could permute those two letters, because no matter where you put them, if you swap them, if you just permute those two letters in those positions, you're going to end up with exactly the same overall looking pattern there. And so that's why we do this. So the answer in this case here is there are only three distinct arrangements here. Okay, if you look up here, there are six of them, but these two are identical, and so are these. There's only three of them. And the way we get that is we take our 3 factorial, the total number of objects, doesn't matter if there's repetition there or not, and then divide by the factorial of the number of items that are identical. I hope that makes sense. What we'll do is we'll go through some examples, and hopefully after a couple of examples that will really make a whole lot of sense to you. Remember, this isn't a restriction that we're imposing on the information. This is just the natural result of having two or more items in this set that are identical to each other.
Determine the number of distinct arrangements of the word economics.
Right, so here we go. So when we do a question like this, what we're going to do here, first of all, is we're going to figure out how many objects we've got total here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 here, okay? And so remember our pattern that we've established here. That means in the numerator, we're going to do 9 factorial. So we're going to permute essentially all of them, regardless if there's repetition or not. Now what we're going to do is we're going to divide by the objects that are repeated kind of factorial. So let's take a quick look here. There's only one E, but there are 2 C's. So I'm going to divide by 2 factorial. There are 2 O's, and actually that's it. So our answer here is going to be 9 factorial divided by 2 factorial, 2 factorial. And so we get 90,720 distinct permutations. Okay? If I just left it as 9 factorial, there would be a whole bunch of those that weren't distinct. Okay? Because swapping, like right now, if I took the O's out and just swapped their positions, you wouldn't notice a difference. It's still going to look like economics. Okay, so that's why we do that.
Find the number of distinct arrangements using all the letters of the word statistics if no other restrictions are applied.
Okay, so once again, now we're starting off with no other restrictions are applied here, implying that the next question that we do here is going to have some restrictions here. But let's take a quick look. First of all, how many letters do we have in the word statistics? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. So we're going to start with 10 factorial. Okay? Now, we're going to divide that by the number of terms that are being repeated. Now let's just take a quick look here. How many S's do we got? We got 3 S's. Okay, so we're going to divide by 3 factorial. What else we got here? We got 3 T's. Okay, 3 T's. What else have we got here? 1A, there's A. We got 2 I's, and that's it. That's the end of it. Okay, so 10 factorial divided by 3 factorial times 2 factorial, and we get 50,400 distinct permutations of the letters in the word statistics. Now, obviously, I think we can tell that we're looking at a restriction next.
A T must be at the front.
Okay, now, and here's that restriction. A T has to be out front. Okay, so how many T's do we have? We've got 3 T's. So that means for my first position, I've got 3 options. Now, once I've made that choice, I really don't care what order they come in beyond that. So how many ways could I order it? Well, there's 9 letters left over, which means there are 9 factorial different ways that could end. Now, but bear in mind that in the numerator here, we're pretending that all of those values, or all of those symbols there, not letters, are unique, but they're not. And so we're just going to divide by 3 factorial, 3 factorial, 2 factorial to take into account the fact that we've got the 3 S's, the 3 T's, and the 2 I's. And when we evaluate that, we get 15,120 distinct permutations of the letters in the word statistics where the T comes up front. Or one of the T's, I should say, comes up front.
Exactly 2 T's must be at the front. The first and second letters are both a T, but the third one is not a T.
Okay, I like this question. Here we go. Exactly 2 T's must be up at the front. Now, this is an interesting question because at face value, it sort of looks a little different than it actually is. Exactly 2 T's must be at the front here. Now, that means I've got to choose a letter for the first position. That's going to be a T, and there are 3 T's to choose from. Then I have to choose a letter for the second position. That has also got to be a T. Now, there are 2 T's left over. But here's the thing. If I'm going to start with exactly 2 T's, that means the third position here can't be a T. So even though I'm referring to just the first 2 positions, this is actually a permutation on the first, a permutation. This is actually a restriction on the first 3 positions. Because in order to get this to work out, I need to make sure that the third position isn't a T. Okay, and when I look at that, there are 7, okay, there are 7 letters there that aren't T. Okay, there's 3 of them out of the 10, 3 of them are T's, that means 7 aren't. Now, once I've chosen those 3 letters, okay, I don't really care what order we put the rest of them in. So how many ways could I order the remaining 7 letters? Well, there are 7 factorial ways you could organize those remaining letters. Now, this is all going to be still divided by 3 factorial, 3 factorial, 2 factorial, because we've still got all sorts of repetition going on there. Okay, now, so what we're going to do here is we're just going to multiply that all out. Now I am going to just go to my calculator and deal with that. So 3 times 2 is 6, times 7 is going to be 42, and then 7 factorial. And there we go. So we get 2,940. That's substantially lower than in the previous question there, but that's because we've now got this restriction on 3 positions, not just the first one. Anyway, please pay really close attention to this particular restriction here, this exactly 2 or exactly however many. Remember that that is implying a restriction on 1 more position than you're being told in the problem.
There must be a C at the front or a C at the back.
Okay, so now we're going to just look at restrictions here. Now, bear in mind that the fact that there's repetition here isn't a restriction. So it's just going to kind of happen in the background here. So now we've got this 3 factorial, 3 factorial, 2 factorial. That is going to be there all the time regardless. Now, there must be a C at the front or I know what or means. Or means addition. Or at the back. So, okay, if I put the C up front, now there is only one C in statistics to worry about, and then beyond that, there's no mention of any restriction here, so it doesn't really matter what order we put those in. So that's going to be 9 factorial, because there's 9 letters. Or we put the C at the back, which means those same letters we're going to permute up front. Now, this is the same as 2 times 9 factorial, all over 3 factorial, 3 factorial, 2 factorial. And when you enter that all into your calculator, you get 10,080.
The 3 T's must be all together.
All right, now the 3 T's must all be together. Now there's a couple of ways that we can approach this one, and what I'll do is I'll kind of outline a couple of things that we could do here. First of all, let's just deal with this the way we would any restriction like this, okay? Particularly if it's got repetition, I'm still dividing by 3 factorial, 3 factorial, 2 factorial for the repetition of everything I've got there. Now, if the 3 T's must all be together, okay, think about what that looks like here. We've got statistics, so that's T, 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 statistics, and there's S, T, A, T, I, C, S. 1, 2, 3, 4, 5, 6, 7, 8. Wait a second. I'm missing a couple of things. What am I spelling? How many? Oh my gosh, 2 I's, 2 S's. Okay, 2 S's, 2 I's. What else am I missing there? 1, 2, 3. Oh, wait a second. There's 3 S's. Wow, I really botched that one. As soon as I start putting the T's up front, I lost all track of the letters there. Let's just double check this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, and there's the 3 S's, the 2 I's. Away we go. Okay, now, if we treat all of the T's as if they are one object all together, okay, now I'm putting a circle around that because, well, actually I should think of it like this. I'm treating them as separate objects here, but in the denominator we're treating them as if they're separate. Let's treat it like this. I've got these 3 T's here, but they haven't said that they had to be in the one order. Now there is only one order for 3 T's, T, T, T. If you change the order, you don't really change the order. But if we treat this as one object, that's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 factorial ways of permuting all those objects. But the 3 T's, if I treat them as if they're different, like we've been doing with these questions like this, that's 3 factorial. Okay? Now, that is the answer to this particular problem here. However, there is another way of going about that. Now, I hope what I did there just made sense here, because remember, here are all the letters. In the method that I just did here, we treat them all as if they're different. So that's why I didn't want to just circle this thing and treat them as one group, kind of underline them so that you see that they're one group here. But again, we're still assuming that they're different. So there's 3 factorial ways of dealing with those T's, and there we go right here. Now, someone's going to notice, well, wait a minute, the 3 factorials are going to cancel. Yes, and let's talk about that. Another way of going about this is to look at this and realize, you know what? Before I just divide by the 3 factorial, 3 factorial, 2 factorial because of repetition. Let's be clever about this and just start here. These three t's, if you permute them, it isn't going to make any difference whatsoever. This is really just like one object all into itself. It's like a gigantic T. Okay, so it is one object amongst this group here. Now, that means that the repetition is irrelevant here because you're keeping them all together. You're keeping them in the same order. Even if you change the order, it doesn't change anything. So this is like one gigantic T. So that means I've got 1, 2, 3, 4, 5, 6, 7, 8 objects here. Now look at the remaining letters. Now you can ignore the T here. I've got 3 S's and 2 I's. So I'm going to divide by 3 factorial, 2 factorial. Okay. Whoops. So I'm going to do this on my calculator here, except I pressed the wrong button. 8 factorial divided by, what do we got there? That's going to be 12. And we get a total of 3,360 different permutations if we keep the t's all together. Now notice these are exactly the same. I just really, in essence, just canceled the 3 factorials. But conceptually, you can think about it as being that those 3 t's, if you're keeping them together, it's really, the repetition is irrelevant here. It's just one big object.
A football team plays an 11-game schedule. How many ways can the schedule end with 6 wins, 3 losses, and 2 ties?
Okay, well, with 11 games, okay, we're going to assume that, and I know this is going to be weird here because there's really only 3 outcomes, but let's assume that there's 11 different outcomes for these games here. How many ways could that possibly be organized? Well, there'd be 11 factorial ways you could organize those games. Now, we're going to break these things up into wins, losses, and ties, assuming that wins, any win is exactly the same as any other win, and the same thing for the losses and the ties there, which means the order of those games that come as a win is irrelevant here. So we're going to divide by the number of ways of permuting the wins, the number of ways of permuting the losses, and the number of ways of permuting the ties. Okay, so we get 11 factorial over 6 factorial, 3 factorial, 2 factorial. Okay, and we're going to get 4,620 distinct permutations. Now, another version of this problem, which is very, there's another one that's very similar, is you've got, for example, a traveling salesman, and he's going from city to city, and he's revisiting certain cities, and the number of ways you can permute his schedule is essentially what we're getting at here. Anyway, similar sort of question, but that's all you got to do. 11 factorial over 6 factorial, 3 factorial, 2 factorial.
All the bulbs for a string of Christmas lights were mixed in a box. Grant was putting the 12 bulbs into the 12 sockets outside in the dark where he could not tell the difference between the colors. If there are 5 red and 7 green lights, how many ways could Grant put the bulbs into the sockets?
Okay, well, this one's actually pretty straightforward. You've got these 12 bulbs here. Treat them all as if they're different. And then in the denominator, we'll identify the repetition here. And there are 5 red, 7 green. So there's 5 factorial ways that you can organize the red, 7 factorial ways you can organize the green, and for all of those permutations of those lights there, you wouldn't notice a difference. And when you plug this into your calculator, you get 792 unique ways that Grant can put the lights out on this string of lights.
How many pathways can be taken from point A to point B, assuming that backtracking is not allowed?
Okay, pathway problems. I'm actually really pleased that the pathway problems have been incorporated into this particular section here, because this really is the place where it belongs. Okay, we used to do these kind of pathway problems in all sorts of different ways, and we do all sorts of crazy things with it, but the intention right now is that you understand this as if it was a permutation of objects with repetition in it. And I know at first it doesn't look like that's what this is. Okay, that's kind of what I like about this. The answer to this question, like how many ways can you get from A to B, is really identical to the number of ways of permuting the letters in a 5-letter word where there's some repetition. And I'll show you what I mean by this. Okay, so what we're going to do is we're going to take any path that goes from A to B. Now, we always have to be moving towards B. Okay, so we start at A, but we've always got to be moving towards B. So that means we either have to be moving to the right or we got to be moving down. Okay, so either right or down in order to get to B. Now, the reason for that is because if I allow backtracking, if I allow, for example, going left or going up here, then I mean I could cycle around here forever and ever and ever and then decide to go. I mean, the number of paths becomes infinite. So we want this to be really quite straightforward. The minimum number of paths if you're going directly from A to B without backtracking here. Now, any path that does that, think about this. Any path that goes from A to B has got to go right once, right twice, right 3 times, and down twice. Now, it can do those in any order you want. We could go down twice and then right 3 times. We could go right, down, right, down, right. It doesn't matter what order you put those in. Hey, hey, wink, wink, nudge, nudge. Okay, permutations. Doesn't matter what order you put those in, but there's going to be 3 motions to the right, 2 motions down. So that's like right, 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 down, down. It's like a 5-letter word, okay, with repetition. So how many ways can we do this? Well, this is going to be 5 factorial divided by 3 factorial, 2 factorial. Okay? So let's just take a quick look here. Okay, I know that 5 factorial, my mistake, is 120. And 3 factorial is going to be 6 times 2 is 12. Oh, the answer here is going to be 10. I was going to go to my calculator and do that, but the answer here is just 10. There are 10, okay, unique paths that take you from A to B. And that's how we're going to approach this. Okay, we're going to take every one of these pathway problems and convert them into words with repetition. So this particular problem here, a little bit bigger, a little bit more going on here. Okay, so now any path that is going to take you from A to B. Now let's not start mapping out all here. Let's just be lazy here. We're going to go along the outside here. So any path that takes me from A to B is going to go right 4 times and is going to go down 4 times. So any path is going to have 8 letters in it. Okay, because basically any arrangement of 4 R's and 4 D's, any arrangement, if I followed it, was going to get me from A to B. So now the question is, how many unique paths are there? So I'm just going to go to the calculator here. That's 8 factorial, okay, divided by 4 factorial, 4 factorial. And the answer is we get 70. 70 unique paths that take you from A to B. Okay, now this final pathway here, notice that we've got individual grids that intersect here at those particular points right there. Now, this question actually could have been asked like this. We could have done this. Made this a huge grid here. And then asked you, said, okay, how many ways can I go from A to B if I have to go through this point here, let's call that C, and this point here, D. You have to go through those points. Well, the truth is, if I'm restricted to going through those 2 points here and I'm not allowed to backtrack, that means none of this extra grid was even relevant, because you'll never get out there. As soon as you get out there, you ruin your ability to go through C and D without backtracking. So because this is what we're going to do here, what we do is we take each individual grid here, and we're going to find the number of ways to go through them and then multiply them together. Because think about it like this. To get from A to B, I have to go A to C and, meaning multiplication, C to D, and, again, meaning multiplication, D to B. So A to C is R, 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 down, down. So right, 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 down, down. So it's 5 factorial over 3 factorial, 2 factorial. To go from C to D, I've got to go right, right, down, down. So that's 4 factorial over 2 factorial, 2 factorial. And I know I'm running out of room here, and this last one is actually identical to that first one. 5 factorial over 3 factorial, 2 factorial. Okay, and when we go to the calculator to determine what the solution is to that, we get 600. There are 600 distinct pathways that take you from A to B, okay, assuming that you have to go through those points of intersection there, C and D. That's about as hard as that's going to get there.
A city center has a rectangular road system with 5 streets running north to south and 6 avenues running west to east. How many different paths from the northwest corner to the southeast corner are there?
Okay. Now, there's a couple of ways that a question like this, a pathway problem, can be described, and you got to pay attention to the difference between them. So we got a city center here. We got this rectangular road system. We've got 5 streets running north and south. So here we go: 1, 2, 3, 4, 5. Okay, and 6 avenues running west-east. So 1, 2, 3, 4, 5, 6. Now I'm a little squished in there, but there you go. How many different paths will take us from the northwest corner, here we go, A, to the southeast corner, B? Now it doesn't really matter kind of which corners you go to, because we're just going to the opposite one. Now here's where this gets a little bit tricky, and you got to be prepared for this. You were told the number of streets going north and south, but a path isn't determined by the number of streets, but by the number of blocks. Okay, so granted, there were 5 streets going north and south, but when I go east here, I'm going to cover 1, 2, 3, 4. Those 5 streets account for 4 blocks where I have to go, and maybe I write this as east. So east, east, east. There are four blocks over which I got to go east. Now same thing, when I go south now to B, those 6 avenues mark off, okay, this is going to be south, 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 south. Those 6 avenues mark off 5 different blocks that I have to cover going south here. Now, this becomes a total of 9 factorial over 4 factorial, 5 factorial, and the answer here, when you plug it into your calculator, is 126. But you got to be very careful when you read it. Okay, that you understand that what we really need to get here, what we're comparing, to get a pathway there, it's the blocks that you cover, okay, as opposed to the streets that are being used to delineate those blocks.
The bakery is 4 blocks south and 3 blocks west of the supermarket. The bakery driver, bored with traveling the same route, decides to use a different route for each delivery. Assuming that he always travels closer to the supermarket, how many different deliveries are possible before he has to repeat a route?
Right, well, here's another question that we should probably draw out first. But this one's been described a little differently. The bakery is 4 blocks south. Okay, 4 blocks south. Okay, let's think about that. See, that's 1 block. Think about it like this. 1 block south, 2 blocks south, 3 blocks south, 4 blocks south. I need 1, 2, 3, 4, 5. Whoops, sorry, can't see that. 5 streets, or 5 avenues, let's say, to mark off 4 blocks south. Okay, here are the blocks. And then 3 blocks west of a supermarket. Okay, so here's my supermarket, and then 3 blocks west. Well, there's 1 block, 2 blocks, 3 blocks. And my bakery's got to be down here. Now, it doesn't really matter that I'm going this way as opposed to this way. It makes really no difference. Okay, any path that takes me from the supermarket to the bakery is going to be going west, 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 and then south, 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 south. So we've got a total of 7 different letters here in the path that we're marking off. Okay, 3 of them are the same and 4 of them are the same. And when we go to our calculators to evaluate that, we get that is the same as 35. So there are 35 unique pathways that take you from the supermarket down to the bakery. And again, just be very clear. In this case, the question told you what the blocks were. For me to diagram that, I have to add 1 more line, okay, so that I can encompass those blocks here. Because for any block, I need 2 lines, okay, to get that block 1 block south there. So if I have 4 blocks, I'm going to need 5 lines. And same thing, if I've got 3 blocks going west, I need 4 vertical lines, 4 north-south lines to demark that. I hope that makes sense.